All right, so let's begin. Again, certainly, please make sure you're keeping up with the reading. At least for the module that I'm talking about, or finishing up today, you should be done with that reading. So keep on working. If you're behind, just keep on working. Read a little bit every day. Okay, so where we last left off, we talk about this idea of indistinguishable arrangements, and we use the example of a population of 1,000 women and 800 men, and the question concerns how many soccer teams you can form where a team consists of 6 women and 5 men. We talked about this idea of a permutation or an arrangement, and that arrangement can be with replacement or without replacement. In this particular case, let me ask you, if you're selecting people for a team, is this arrangement that you form of 6 women and 5 men, is that with replacement or without replacement? Without replacement? So let's think, did I hear without? Without. So let's think, thank you for answering. So let's think about how you select people for a team. Now, let's say you pick the first woman for the team, doesn't matter who she is, but it's intramural or soccer, whatever, tournament, what have you. You start with a population of 1,000 women, and you pick the first woman for the team. How many women do you have left for consideration after that? You have 999, okay, because once you make that first pick, she's on that team, and she can no longer be considered the next time you pick a female teammate or team member or member of the team. So let me ask you again, is this with replacement or without replacement? It's without replacement, right? And so without replacement means that when you make a pick for some selection, that that particular pick reduces the size of the population, is no longer considered in the population the next time around. And this problem, in terms of picking a woman for the team among the 6 total women on a team in this example, is similar to the 3-on-3 football team example. Once you pick some object or item or person, you no longer have that member of the population available for consideration for the next pick. Okay, and so in this particular case, you're making or forming an arrangement without replacement, and as such, you want to find an arrangement of 6 women, because that's what the problem asks, and 5 men that together form a team. Now, of course, in this case, let's say the first woman you picked was Mary, and the second was Susan, and the third one was Mev, or pick some names. Now, if you have Mary, Susan, and Mev, right? Does it matter which comes first? If it's Mev, Susan, Mary, or Mary, Susan, Mev, does it matter? Does it matter? No, it doesn't matter. All that matters is the membership or their membership among the 6 women that you're going to pick to comprise this 11-person team. So in that particular case, it's indistinguishable. But when you make a pick, right, you're picking without replacement, but the particular choice should be indistinguishable. And so if we look at this expression for combination, we can write it a few different ways. We have C of nk, right? That's called combination of n items total, pick k. C and k, my pen doesn't work. Okay. Okay, I'll use my finger. I think my pen ran out of batteries. So if we look at C and k, that's one way of writing it. N with this k below it, that's n choose k. That's another way of writing it. And if we look at this expression, we'll see that the permutation or the arrangement without replacement, that's this n factorial over n minus k quantity factorial. I'm not as dexterous with my finger versus the pencil. It looks like it ran out of power. And so this extra 1 over k factorial is doing is taking account for the fact that once you pick these 6 women, you can arrange those 6 women in different orders. So you could have Mary, Susan, Mev, you could have Mev, Mary, Susan, and so forth. And so what we're going to do is develop this expression, uh, relating it to this permutation, and we're going to add a fix-up to account for the fact that you can have multiple arrangements of those individuals that you pick. Okay, so there we go. So in this particular case, if you pick 6 women, you have 6 factorial many arrangements of the 6 women that you pick, regardless of which ones, right? So I'm just going to label them, or you could label them W1, W2, W3, W4, W5, and W6. Now, because you have 6 of those items, you can arrange them in 6 factorially many ways. And where that 6 factorial comes from is that you have 6 choices for the first one. Let me see if I can write with my finger. 6 choices for the first one. It's not letting me. 5 choices for the second one. 4 choices for the third one. 3 for the next one. 2 for the next one. And 1 for the last one, right? And so what you do is you take this 6 factorial and you use that to account for the fact that you have that many arrangements of the 6 that you pick. And it doesn't matter what order the 6 women you pick and what order you pick them. What matters is their membership on this team, right? And so when you look at the number of arrangements using this permutation or this selection without replacement, you have to account for the multiple ways that you can pick or arrange the 6 women for this particular team. So you can have them in 6 factorially many arrangements. And what you do then, we have our expression, and I really wish my pen had power. No, I don't have power. Nope. All right, I wasn't expecting this. All right, so let's just go on. You have this expression, P of nk, which is the number of arrangements of k items chosen out of a total population of size n, and that is without replacement. And so for the first pick, you have n many. For the next pick, you have n minus 1. And next pick, you have n minus 2. It reduces by 1 each time you make a pick. It's without replacement. And then for the last pick, you have n minus k plus 1, right? So you multiply these together, right? And that's essentially the same expression as n factorial over quantity n minus k factorial. Now you take that expression, and that expression treats Sue, marry, Mev the same, as different rather from Mev, marry, Sue, right? So you have to account for those 6 factorially many duplicates, if you will, because the order is indistinguishable. So to be correct, you're going to take our k factorial, the number of arrangements of the 6 women, and you're going to divide that expression for permutation without replacement by that k factorial. So if you do that, you get this expression, n factorial upon n minus k quantity factorial times 1 upon k factorial. Okay. Any questions about this? Does that make sense? Okay. So you're basically taking this expression for selection of k items out of a population of n where it's distinguishable, and you're making it indistinguishable by dividing by the k factorially many arrangements of those 6, in this case that you've chosen. So we can do the same thing for men as well as for women. So in that case, if you're selecting 6 women out of a population of 1,000, that would be n factorial, 1,000, over n minus k factorial, 1,000 minus 6 quantity factorial, times 1 over k factorial, in this case 6 factorial. You can do the same thing with the men. So if the question asks, out of a population of 800 men, you're going to choose 5. That would be 800 factorial over quantity 800 minus 5 factorial. So that's n factorial over n minus k quantity factorial times 1 over 5 factorial. Okay? And so we multiply these two terms together. The first term is for the 6 women chosen out of 1,000, indistinguishable arrangements. And the second term corresponds to the 5 men chosen out of 800, indistinguishable for those arrangements. Okay. We'd multiply these two terms together, and there's our answer for the number of teams we can form given these specifications: 1,000 women choosing 6 and 800 men choosing 5. Right, any questions about this? Okay. So we could rewrite this expression mathematically in terms of how we'd write the expression for combination. And we get this. That's 1,000 choose 6 times 800 choose 5. All right, so that's just another way of writing it. In the previous slide, I'm writing it out in terms of the mathematical definition. Okay. Any questions about this? Make sense? Okay. So let's look at some identities. There was a typo in the slides that I corrected while I was in my office. I'll repost them this evening after my last class. But there's the definition of what so-called combination is. So it's the indistinguishable arrangement of k items selected from a population of 100. That's n factorial upon n minus k factorial times 1 upon k factorial. If we took n, choose 0 items, there's only one way to do that. Now, mathematically, if you plug that in, that would be n factorial over n minus 0 factorial, which is just n factorial, times 1 over 0 factorial. 0 factorial is just 1, right? So that would be n factorial over n factorial, and you just get 1, okay? If you were to look at n choose 1, right, that's just n. And if you think about it logically, well, if you're trying to choose one thing out of n, population of n, well, there are only n different ways you can do that. But mathematically, you can plug in into the formula for combination, and you get n factorial over n minus 1 factorial, n minus k, times 1 over k factorial, which is 1 factorial, which is 1, right? So you would get n times n minus 1 times n minus 2. You would cancel, right? So that would be n factorial over n minus 1 factorial times k, times 1 factorial. Now, n factorial is just n times n minus 1 times n minus 2 times n minus 3, and that's the same as having, oh, I can't write. No, fingernail isn't working. Okay. That would, the n minus 1 factorials would cancel in the numerator and denominator, and you would get n resulting. Okay. Next time I'll charge my pen between classes. Likewise, and you can try this out with the math, and I recommend you do that to convince yourself, n choose k is the same as n choose n minus k, right? If you plug in, things will cancel, and you get the same expression. Okay. Any questions about this? All right. So let's take a look at combination with replacement. This is the with replacement version of it. And unlike combination without replacement, this is more like that color palette example. Now, with the color palette example, we had 8 crayons, and we were choosing or constructing a color palette of 3 colors. And it was the case for that example that when you made a choice, you examined it and returned it back to consideration by the next chooser. And so the number of items available for selection from one round to the next did not change. Okay? And so the question is, how would you do this combination, the construction of arrangements of k many things given a population of n, where you're making these selections of k things with replacement. You're examining it and returning it back for consideration. Now, for something like a team, if you're forming a soccer team, you're not going to do with replacement. For something like a color choice, that's going to be with replacement. So anytime you're given a problem where you're trying to count or evaluate the number of arrangements, it's important to ask yourselves these questions. When you form an arrangement, is it with replacement or without replacement? Are these arrangements distinguishable or indistinguishable? And so there's a clever construction that's done in order to form this expression. Now, when you're when you have a population of n things, the construction goes is that you form these n slots. And how you form these n slots is using n of these bars, n minus 1 of these bars. So here we have some vertical bars. You can think of these vertical bars as sort of the walls of a bin, right? So you can imagine if I had like a bucket or bin, right? And each one of these bars separates one bin from another. And if you have n categories or n total choices, you need n minus one of these bars to separate those n many bins. So let's take, for example, if you had three categories, right? If you had a population of size 3, you're going to have 3 bins, and therefore you're going to have 2 of these vertical bars. So if you only imagined 2 of these vertical bars and there's nothing else here, well, you'd have one position representing the first population member, another position between the 2 bars representing the second one, and then another position to the left of that left-hand bar representing the third position. So if you have a population of size n, each one of those populations or those choices is represented by a space, and different spaces represent different members of that population from which you can choose. Does that make sense? Does that make sense? Question? So if you have n choices, a population of n, you're going to have n minus one of these vertical bars. Now, in this construction, each of those things you're using to make an arrangement with, the k of them, right, is represented by one of these balls. And so when you select with replacement in constructing your arrangement, let's say, category or population member 1 represented this space to the left, your left of this vertical bar. If you chose it, wrote it down, put it back in consideration, and then you chose it again, when you're sampling or choosing with replacement, you can make multiple choices of the same color if it's a crayon, right? You can choose purple and then purple again, right? You can have repetitions. And so you mark each of those k choices with one of these balls that's in one of these n many positions, and each of these n many positions is to the left or to the right of one of these n minus 1 bars. And it's n minus 1 bars because you need n minus 1 bars to mark n different positions. So in this example, you'll see in this first position, this left-handmost position, there are 2 of these yellow balls in that first position, and that represents having that first member of the population selected twice through this sampling or selection with replacement. Does that make sense? Any questions? So what this construction is doing is it's depicting the fact that you have a population by noting n spaces to the left or the right of one of these bars, and then each of those k many choices out of that n is represented by a position for these yellow balls, and the number of choices for that population member is depicted by drawing these balls in one of these n different locations. Okay, so in this diagram here, we've picked this first individual twice, the second individual once, the third individual no times, the fourth individual we selected 3 times, the fifth individual none, sixth none, seventh twice, eighth once, and everything else none. Okay, that's what this particular configuration represents. Now, of course, how you depict the combination with replacement is now asking yourself, given all of these items, what are the number of indistinguishable ways I can pick k of them? And that's literally what combination with replacement is doing. So we have a total of n bars in this arrangement, n minus 1 bars representing the n positions. And then we have a total of k balls, okay? So out of those k plus n minus 1, we're trying to pick k of them. Because when we pick k of them, that's going to give us our combination with replacement. So the construction itself is an aid for trying to use indistinguishable combination as a means to encode this particular scenario where you have selection with replacement. So previous slide is combination without replacement, right? Indistinguishable arrangement. The next slide, you're adding these bars to encode combination with replacement. Okay? All right. Any questions about this? I wish I had my pen working. I didn't charge it between classes, so I don't have my pen. ready for use. All right. Please try this yourself. Try it as an exercise yourself, and I will show you some MATLAB that'll help you do this. Okay. So let's take a look at our MATLAB. There are two API calls. One's called perms, that's permutation, right? That's selection without replacement. And then there's n choose k, that's indistinguishable arrangement of k items from n items. Okay, so let's do that. Perms and n choose k. So I'm gonna turn off the mirror and go back to my laptop and let me run MATLAB. And so the first thing you should do, type help, perms, permutations. So all possible permutations. So you can give it numbers. You can also give it a cell array. And if you give it a cell array, it'll tell you the actual uh, arrangements. It'll show that to you. So let's say if I said permutations, perms, of number of permutations of say 3 things, right? So that's 3 times 2 times 1, right? So if we look at that, it gives you, for numbers 1, 2, and 3, all of the 6 many permutations that you can have of those 3 objects, 1, 2, and 3. I can create a cell array, values equals, let's say, Sue, oops, Mary, and say Mev. Okay. So now if I said perms, vals, it shows me those permutations or arrangements of Mev, Mary, and Sue. Those are distinguishable arrangements. Okay. Any questions? So I could use numbers. I could also use objects in a cell array. Now, these numbers, that's pretty useful. Let's say if you had an array of objects and you wanted to find those arrangements, it would give you the indices, index 3, index 2, index 1, 3, 1, 2, and so forth. So let's take a look at the other one and choose K. So if I type help and choose K, those are indistinguishable arrangements. It's also called the binomial coefficient. We'll talk about that later in the semester. It says n choose k, the first parameter is n, the size of the population. K is how many things that you are selecting. And it says it returns n factorial over n minus k factorial times 1 over k factorial, many things. Let's try this n choose k and give it some values. So let's say n choose k. And let's start with small numbers. 3 is the total size of the population. And let's say you're choosing 2 things out of a population of 3, right? There are 3 different arrangements. Now for n choose k, it's for numbers, it's not going to give you the listing of those choices. It's just going to write the answer. For cell arrays, let's say vals, we had before, Sue, Mary, Mev. I can say n choose k, vals, which is that cell array, choose 2. So here they are, Sue and Mary, Sue and Mev, Mary and Mev. And you can see that it doesn't matter what the order are, they're indistinguishable, right? So we could have something like, n choose k. We could have something like cards, and I'm not going to do all the cards in a deck, right? It takes too long. There's ace, jack, king, queen, 10, 9, 8, 7, 6, 5, 4, 3, oops, and 2. Hopefully I didn't miss anything. Ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. Okay, so now you can say something like poker hands is equal to n choose k cards, and I'm not going to do a full deck, just 13 because it takes too long to write 52 items. And you choose, was it 5 cards in a poker hand, right? So now, if I do that, it gives me all the different poker hands that I can form, and there are quite a few of them. I can take the cardinality of that, look at the size of that array, and tell me, how many rows there are. That's the total number of combinations. Okay? All right. So if I have a cell array, I can enumerate all of the different uh, indistinguishable combinations. If I have a number, it'll just tell me what those numbers are. Or you could calculate those from the formula for combination. Okay. Any questions about this? Does that make sense? Now, of course, if you have a large number of things, MATLAB, it'll try, but you can easily run out of space, right? Even if you have a lot of RAM on your system, because n factorial can get pretty large when n is very large. Okay? All right. No questions? Make sense? Okay. So let's exit MATLAB and let's bring up the next module. And I think I'm just going to do the clicker with this from the laptop from start. I think that's 5. Start. Okay. So let me unplug that and put that in. All right. So let's segue and start talking about conditional probabilities. So the reading has changed, right? So you should be caught up in your reading by now. And so please make sure by next week you're reading the section 2.4, which is just a few pages, but I can appreciate the fact that the material is very terse, and you're going to need to go off and look stuff up. So please make sure that you're staying up with the reading, read like a ninja, and do it every day, right? By doing it every day. Okay, or study like a ninja. All right, there we go. So I'm not going to play the video from last time. There's the URL from YouTube. Just want to avoid further copyright disputes. And we talked about this idea of equally likely outcomes in counting. If you have an event that is the combination through union of a set of other events, you can compute the probability of that complex event by summing together the individual probabilities of each of these singleton events. And so in any sort of probability evaluation, this when can I see you again, when will this event occur, what's the proportion of trials or experiments when this event will occur again, you compute that as the number of favorable outcomes, what you're looking for, divided by the number of total outcomes. Both of those requires counting. Okay. We also talked about considerations for counting. You ask yourself a number of questions. 2 of them are major ones. Do I replace after selection? So that with replacement, or without replacement. Without replacement, the example for that was the 3-on-3 football team. The with replacement, the example motivating that we use is the crayon example for forming a color palette. The other consideration is if you distinguish duplicates or not. If you do not distinguish duplicates, you have to account for that in your counts when you make an arrangement. If you do distinguish duplicates, you have to compute the number of arrangements. We talked about permutation, and we talked about a fix up the permutation to account for indistinguishability when we discuss combination. And then we also have a with replacement version of combination that we use by introducing this idea of these vertical bars, or these sticks that mark all of the members of the population from which you're making a selection. Okay. Any questions about these? No? All right. The screencasts are also up if you choose to review the material, and that's new this year. Okay, so let's do a little bit of a warm-up. Now, there's this notion of a random variable. We talked about events, but now we're going to kind of bend our thinking a little bit to develop machinery that we need we'll need when we get to distributions. And so we're not going to talk about events going on. We're going to talk about this idea of a random variable. And a random variable is a quantity that measures something over your observable event. Now, the thing that you're measuring could be the raw event itself, or it could be something that you're asking about the event. So when we said you flip a coin n many times, we counted the number of outcomes you can have, which was 2 to the n, for all of the different ways you can flip a coin n many times, what those outcomes are. Now, a random variable might be you're measuring the number of heads. What's the probability that when you flip a coin n times, that the number of heads will be greater than 3? That's an example of a random variable. A random variable measures something over the event. And so one question this measurement can encode is how many of a certain type of object do you have, or a certain type of event in some complex event. It also could be how much does something occur. So let's define an example, and we use this as a warm-up to motivate this idea of a random variable. And then once we get that machinery in place, we're going to take a look at so-called conditional probability, which I also like to call a filtering probability. So let's define t, and t is a random variable. And this particular random variable is going to measure the number of tennis balls of a given color that are picked from a particular bin. And we'll have the visual for the construction in the next slide. So here we have a bin. And let's say in this bin, and I have to show it to you for the sake of argument, but if I were doing this for real, you wouldn't be able to see inside this bin. It'd be a bag, and it would be opaque, or you'd be blindfolded, or close your eyes without looking into it, and you'd reach in and you'd grab a ball, right? And so we have some number of balls. In this particular case, we have 12 balls, and some number of these balls are yellow tennis balls, and some number are green tennis balls. Now, of course, when you compute the probability of a random variable, you want to know what is the probability or the likelihood on a 100% scale that you will have a particular item of a value that you desire. Now, that desired item is called your favorable outcome. What do you want to see as the outcome returned by this random variable? And then the other quantity you're interested in is the total number of outcomes, right? Both of those require counting. The bottom requires cardinality of all the possible events that you can observe. So how you express this probability is the number of favorables, items of a particular desired value, where the value is outcome of your random variable. And it could be equality, it could be greater than, it could be less than, it could be a combination of things. And the denominator is the total number of outcomes. So let me ask you, for this example, what is the probability that when you reach into the bag, not preferring any one of the other, that you're going to pick a yellow? What's the probability? The five. So 5 over, I heard 5 over what? The over 12. 5 over 12. So 5 green, 5, how many yellows are there? So for yellow, there's 6, right? No, 7 yellows. So 1, 2, 3, 4, 5, 6, 7, right? And how many total? A total of 12, right? So 7 over 12. So then what about the probability of picking a green, right? So I heard 5 over 12, right? 5 over 12, because we have favorable, that color attribute, there are 1, 2, 3, 4, 5 that are green, and we have a total of 12, so that'd be 5 over 12 green. Total items. Oh, I'm sorry, that's not minus, that's total dash items. Yeah, that's a poor choice of font that I have. So yes, that's total items. I should do underscore, but yeah, that's a bad font. All right, yeah. So we have 7 upon 12 for the probability of yellow, and we have 5 upon 12 for the probability of green. Now, of course, knowing that there's only green or yellow, you could just take 7 over 12 and subtract that from 1. So you could say 12 over 12 minus 7 over 12, right? And arrive upon the same conclusion based on the law of total probability. Okay, all right, that's good. So let's make it a little bit more complicated. So in this construction, I'm going to group my balls into regions. And let's assume like we had multiple bins. And some of the balls are going to be in this first bin. I'm going to mark that as bin 1, right? The next one is going to be bin numbered 3. And the next group of balls, bin 5. And that last ball is going to be bin 7. So you can imagine I went out and I bought some yellow tennis balls. and then I wrote in big magic marker on each ball. For 4 of the balls, I wrote a 1 on them. For 9, 10 of the balls, I write a 3 on them in magic marker. And then maybe for this 5 balls, I write 5 in magic marker on those. And then for that last ball, I write 7. So imagine I took these balls and I wrote these bin numbers on each of the balls to note where did it come from. And then I took all these balls and I put them in a bag that was opaque to you, right? And now I'm going to ask you to reach into this thing and pick out a ball. And we can actually now work with these probabilities that you're going to choose a ball that has a certain number written on them. Okay, so again, let's try this exercise. If you were going to pick a ball and these balls were labeled 1, 3, 5, or 7, right? The balls from each of these, and they're all put in a bag. You reach in the bag and you pick one. What's the probability that the bin number marking on these balls is going to be a 3? What's that probability? Again, we follow this recipe. The number of items that you want of a particular value, right? So we'd go through and you look at all the balls and you count the number that have a 3 marking on them. So you say, is that a 3? Nope, 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 nope. Oh, these are all 3s. There are 10 of them. So the number of favorables is 10. Is that? Nope, 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 nope. Okay, the total number is 20. So you would have 10 over 20, or 0.5, 50% probability that if you reached into this bag with the balls with markings written on them in this fashion, that you would pick one that has a 3. So it's 10 over 20. That's 1 upon 2 for a probability of 50%. Okay, so again, we're just literally following the process, right? Nothing magic here. No, kind of eyeballing it, but just blindly following the recipe. Okay, any questions about this? Okay, so now let's say we did something a little different. We have some of the balls are yellow, tennis balls, and some of them are green. And again, we're going to take a black magic marker and we're going to write on these balls a number. So these balls, we have some yellow and we have one green. We have 9 yellows here, 2 green, 3 yellow, and 1 green. So we have those colors for balls, and all the balls from the first bin are going to have a 1 written on them. All the balls from this bin are going to have a 3 written on them. All the balls for this bin are going to have a 5 written on them. And lastly, the ball here is going to have a 7 written on it. So you take those balls, and now there are 2 different attributes associated with these balls. Each ball has a color, and each ball has a number written on it. And so it could either be green or yellow, or the number written on it can be 1, 3, 5, or 7. So let's say we have a random variable, t, and t is going to measure the ball color. And so one question we could ask is, what is the probability that when you pick one of these balls out of a bag, you take them out of the bins, throw them in a bag, they have a color or a number written on them, what's the probability you're going to pick something that's a green ball? What is that? So how many favorables do we have? How many greens do we have? We have 4 greens. And how many total do we have? We have 20, right? So we express number favorable over the total. So that's 4 upon 20, which is the same as 1/5 or 20%. So it's a 20% probability that we're going to pick a ball that's green from that bag. Okay, good. So now, what if we were only concerned about some of the bins, but not all of the bins? In this case, our universe of consideration was across all of the bins. So we looked at balls for the total, that denominator of this expression, total items. We looked at every single bin, and we counted all the balls in every single bin, regardless of color or bin marking. Okay? But what if we're only considering or concerned about some of the bins, but not all? And this idea of considering some of the bins is called a conditional probability. You can think of it semantically as a type of filtering probability. And when you see conditional probability, you see an expression like this third bullet point, the probability that some random variable equals a value, and this vertical bar, you pronounce it given that a second variable is equal to another value. And so what that right-hand side of that bar, that conditioning bar, the given, it says that you've seen something, you have more information. And what that information does for you is it changes your universe of consideration. It changes the denominator in that expression, number of favorable over the total number. If you have more information, what that tends to do is change, or in many cases, improve your probability, right? And how you implement this is you start out with your condition variable, and your condition variable, given variable 2 is some value, is considered something that you've seen. It's new information. So you take this piece of information that you're given variable 2 equals other value, and you use it to filter out or reject all of the objects that do not satisfy that condition. What you're left with is a reduced version of your universe of consideration. So then once you've filtered out things that do not pass this test, right, you're only left with conditions or objects that pass this test measured by variable 2. You now calculate the probability of the favorable, for the favorable. Okay? So let's take a look at that with this balls and bins example. So let's say I was doing this experiment and we had these bins, and these bins had balls of different colors, so we're dealing with two attributes. And then balls that came out of bin 1 had a 1 written on them. Balls that came out of bin 3 had a 3 written on them. For bin 5 had a 5 written on them, and bin 7. So we have two different attributes. We have a bin number written on the ball, and that's the bin it came from. And then we also have a ball color, which can be yellow or green. Okay, so I take all these balls and I blindfold you. And let's say, your friend whispered in your ear and said, hey, by the way, I saw Holness only pour out bin 5, right? That would be given that the bin is known to be bin number 5. Now, would that change the probability? Why do you think it would change the probability? Would it? Would it not? No, it would certainly change the probability. And how it would change it is now when you compute the total number, you no longer are considering all 20. Knowing this piece of information that you saw me pour out only from bin number 5, you know that only these balls are now in that bag. So this piece of information meant something to you, and it's going to result in changing that probability. Now remember, when we calculate the probability of green, if we didn't have this extra information, you said 20% probability, and we computed that. Now we'll see that the probability increases because you have extra information. Okay, so let's try this out. If you knew, given bin 5, you'd go through your universe of consideration and you'd say, okay, is this bin 5? Nope, throw it away. Is this bin 5? Nope, throw it away. Throw it away, throw it away. Everything here gets thrown away because its marking is not 3 written on the ball. So now here, yes, you're going to keep this, keep this, keep this, keep this, keep this. This one, the bin number says 7 written on it. And I really should bring in balls, but I didn't want to buy 20 tennis balls. But the bin number says 7. It's not bin 5, so I'm going to throw this away. So all you're left with now is 5 balls, those that are poured in from this bin. So that piece of information about given the bin measurement for the random variable equals 5, it's now going to change the denominator of that expression. Okay, so given that it's bin 5, we know that total items is going to be 1, 2, 3, 4, 5, and no longer 20. So then if we evaluate the probability of getting a green, right, given bin equals 5, well, how many greens do we have now left with this altered universe of consideration? We have 2 green balls out of a total of 5 balls on this modified universe of consideration. So that's now 2 upon 5, which is the same as 40%. Okay? So it'd be 2 over 5, or 40%. And you'll notice 40% is twice as much as the probability that we had before without this knowledge of the bin equals 5, which was 20%. Okay? All right. Any questions about this? Does that make sense? Okay. So you might be asking, well, why the hell do I need that? Why? Why do we even do that, right? Why would you care? Well, this is called a conditional probability. And a conditional probability allows you to express this idea of in light of new information. If I get new information, have a new observation, a new piece of information, it'd be nice to be able to update your probability. And that's precisely what conditional probabilities use. Now, the new information certainly can change the probability, and it's very useful to be able to evaluate what your probability changes to if you got a new piece of information. And this is used all over the place. And I'll show you a couple of simple examples in a few slides. So this is called a conditional probability, and it's expressed as the probability of some event given this vertical bar, given the observation of some other random variable. Now, if those two random variables are related from an information perspective, this is going to change that probability that you would evaluate of just the event without any other observation or piece of information. And so how you pronounce this expression, P of E given A, is probability of event E given that we observe some other event A. Okay? All right. Any questions about this? Okay. So let's suppose in an example, and remember that when you evaluate a probability, it's only based on the observations that you make. You can only observe based on observations. Now, suppose each week, right after class, you always went to the campus center for lunch. And let's say every class, you stepped outside and a pack of wild dogs started chasing you, right? And it happened without fail every single week. That would kind of not be pleasant. So let's say probability of the dog chasing you, you have some sample space omega called omega dog chase, and it could be value yes or no. Okay, that's fairly simple. And let's say for each week during the semester, for the first 9 weeks, every time for the first week, for the second week, for the third week, up through the 9th week, every time you set foot outside, a pack of wild dogs chased you. Okay, well, at that juncture, your probability of being chased by a dog after this class, and I hope a dog doesn't really chase you after the class. I have no control over that. It's just an example. It would be 100%, because at this juncture, that's all the information you have. Every single week, 9 times out of 9 weeks, you were chased by a dog after this class, right? So from the perspective of this system, right, because you don't know what the true probability is, all you know is based on what you observe. But from the observations here, the probability of being chased, that yes outcome is 100%, and that no outcome by law of total probability is 0%. So then let's say the 10th week, you very, pensively kind of slowly walk outside and you step off of the staircase and get ready to go to the campus center. And all of a sudden, on the 10th week, there's nothing, right? So in light of that new information on that new observation, so after 9 weeks, you know 100% that it's going to happen. On that 10th week, you get a new observation, you look around, all of a sudden, oh, wait a minute, nothing happened. There's no pack of wild dogs. So all of a sudden, in light of this new information, the probabilities have changed. Given that 10th week's observation, now your probability changes. Dog chase is now 90%, yes, is 90% for that event, and for no, it's now 10%. So this idea of being able to update your probabilities in light of a brand new observation is really, really important, okay? So I promise you it's very important. How important is it? Well, you've been using it quite a bit. When you do voice recognition, what you're evaluating is the probability of the next word that's uttered given the sequence of previous words. When you use autocorrect on your phone, right, it's computing the probability of that next word given what all the previous words are. So if you type a sentence on your autocorrect, you'll notice it gives you like 3 different suggestions, right? It's calculating a probability of what the top 3 next words should be given all the previous said words were. So, you can just kind of mess with your autocorrect, right? You can just start typing some sentences, right? And type some weird sentences, right, that don't make any sense, and then try to type the next couple words, and it'll start using that weird following word based on what you've typed. And then over time, or based on the text message conversation that you're having, it gets usually pretty good at predicting the next word because people tend to have habits or particular styles in which you like to write, or when you're talking about a certain subject, you usually string along a bunch of different words together, and that isn't random, right? There's a particular set of words that tend to co-occur with one another, right? So autocorrect and voice recognition, like Siri and Alexa and all those things, they're absolutely using these conditional probabilities, and it's trying to calculate the probability of the next word given a sequence of previous words. Weather forecasting, hurricane tracks, right? You notice when you see on the news hurricane tracks, they have all these kind of different lines that go and they're kind of close by one another going in some direction. Well, what they're computing for weather is the probability of rain or a certain weather event given the number of days of previous weather, right? With the hurricane track, given the previous locations that this hurricane moved, the probability of what the next location of the hurricane will be over a certain amount of time. And you'll notice when they say a hurricane is approaching, and they'll say in 1 day this is where it'll be, in 2 days, in 3 days this is where it'll be. You'll notice as the number of days in the future increases, those lines get further and further apart, right? So what they're doing is computing these conditional probabilities. What's the probability of the new location of that hurricane given the previous locations of that hurricane? In robotics, we use conditional probabilities all over the time, all the time, all over, all the time, for something called localization, right? So your measurements are things like your camera and your GPS and your LiDAR range measurements. And what you're trying to calculate is effectively a conditional probability, the probability that you're in a certain location given the sequence of previous locations, right? And that's literally how Monte Carlo localization works. That's how autonomous driving works, right? They also have, excuse me, um, the um, the GPS gives them a lot of leeway because they can look at positional information quite accurately. But literally in navigation and in localization, trying to figure out where you are in the world is just a plain application of these conditional probabilities. So it's used all over the place. These aren't the only places. This is just a very, very small sample of where this sort of thing is used. Okay, and so you can make a career out of just computing conditional probabilities for various contexts. Okay, all right. Any questions about this? No, all right. So how we would define this, and this is in the book, a conditional probability, probability of A given the observation of event B, knowing that B is going to occur, what is the probability of A, right? And it's pronounced probability of A given B, right? So this is defined in the book, and there are other definitions out there, excuse me, if you look at other pieces of the literature. So we talked about this idea of a probability as being the number of favored events measured by a variable over the total number of outcomes. So here is a Venn diagram, and we have our sample space omega listing or enumerating out all the possible observations you can have. And then we have some subset of that we're calling event A. So if we're going to compute our probability of A, that's the number of outcomes in A divided by the total number of outcomes in our omega. So when we have a conditional probability, we're doing something very similar to that, but as I said before, you're changing your universe of consideration. When we had no restrictions on A, we had no other information about B, and that could influence A, our denominator was this entire sample space omega. But let's say we have a second event B, right? And you observe B to happen, that's an extra piece of information. So the question that you're asking with a conditional probability is what is the probability of event A now that I have this new knowledge that B had happened? And when I know B had happened, I'm no longer looking at the entire sample space omega for my universe of consideration. I'm looking only at B. So I'm changing, I'm shrinking down, if you will, the universe of consideration down from omega to some smaller set of omega that coincides with event B. Now, of course, you'll see that B overlaps with A in this case. And the definition for the conditional probability, probability of A given B, is nothing more then that overlap region where A and B intersect divided by B. Now, if you think about it, if you look at this numerator, the favorable event, it says probability of A, right? Now, of course, if you're only considering that portion of your sample space that coincides with B, you're no longer looking at all of this yellow portion. You're only looking at, for the probability of A, that part of A that occurs also within B. Because you said, given that B occurs, right? You're changing your universe of consideration. So here, the portions where A occurs is in that intersect region. And then we divide by our new universe of consideration, which is B, right? This region. Now, you're given that B occurred, so you can only consider as your total set of outcomes, you can only consider all of that that occurs in B because that's given to you. You observe that. That changes your universe of consideration. So we have probability of A given B is the number of outcomes in A, that intersect region, divided by the total outcomes, which is modified from omega to be that region in B. So we get that expression, probability of A and B, divided by probability of B. Okay, so there's our definition. Any questions about this? Questions? No? Make sense? So when we had that balls and bins example, you said given that the bin number was 5. And so you said, okay, well, I'm only going to count my favorables knowing that it only came from bin 5. You're changing your universe of consideration, but it's still just the number of favorable events divided by your total outcomes, but your total outcomes has shrunken because you have new information. Okay. So we're given B, and so because we're given B, we know that our total outcomes are only limited to B. Because if we said something outside of B, well, that doesn't satisfy this given B. So what this filtering probability does, when you condition and you say given B, you're limiting the total number of outcomes. You're recomputing it. So let's take an example. Suppose I were to roll a die, and I were to ask you, what's the probability of rolling a 2? And you would say, okay, well, there's only one event called a 2, and I have a total number of outcomes. There's 6 of them. So it's a probability of one item divided by 6. That's 1/6. Okay. Now, if I were to tell you, gosh, well, I know that it was an even that was rolled, right? That changes your universe of consideration. So instead of considering all the outcomes of a die, 1, 2, 3, 4, 5, 6, you're now looking at the evens, 2, 4, 6. Your universe of consideration changes. So now you look at your new universe of consideration, the evens, so it's 2, 4, 6. There are 3 of them. And how many of them are 2s? 1 of them. So you say 1/3 for 1/3. Now 1/3 is bigger than 1/6. You've now increased your chances because you've incorporated new information. And again, your universe of consideration has changed. Okay, so let's say you have a deck of cards, and this kind of gets to poker. And you have 52 cards in a deck, and those are ace, king, queen, jack, 10, 9, 8, 3, 9, 8, 7, 6, 5, 4, 3, and 2. And then each of these 13 cards can come in one of 4 different, I think it's called suits. Spades, hearts, diamonds, and clubs. So you can have ace of spades on through the 2 of spades, ace of hearts through the 2 of hearts, ace of diamonds through 2 of diamonds, and ace of clubs on through 2 of clubs. So 13 times 4 is 52, right? So you have 52 cards in a deck, and let's say you're playing a poker game. And, in this poker game, you might ask, before the dealer hands out cards, what's the probability of getting a king? Well, you have 1 king in each of these 4 suits. So that's 4 kings out of 52. That's 1/13 probability, right? Okay. Now let's say the dealer starts dealing, and the dealer deals 3 cards out to somebody, and dealer deals a jack, a queen, and a king. Well, given that you saw a jack, queen, and a king, and let's say, it's a jack, queen, and king, it doesn't matter what the suit is, well, your universe of consideration is going to change. So you had 52 cards, so now there are 49 cards, because the deck is now missing 3 cards because 3 cards were given out. Now, if you put out a king, a queen, and a jack, well, let's say they were all spades, right? The jack of spades, the queen of spades, and the king of spades were put out. So now that means you only have a jack of hearts, diamonds, and clubs. You only have a queen of hearts, diamonds, and clubs, and you only have a king of hearts, diamonds, and clubs. So then if the question is, after seeing these cards dealt, a king, a queen, and a jack, what is the probability that a king is going to be dealt out next? Well, how many kings were dealt out? You have 1 king. It's 49 cards left, and 1 king is gone. So now you have 3 kings out of 49 cards, or 3 over 49, right? And so let's say you're playing a poker game with 2 other people, and you deal 5 cards to each person, right? The probability of certain things happening, you can actually calculate off the top of your head because the deck of cards doesn't change. You get used to it. You can actually run these numbers in your head and decide, gosh, well, should I bet knowing that this person has this card or that person has that card, right? It's absolutely doable, and it's just an application of conditional probabilities, right? So we're going to have at some point some exercises. We're certainly going to have a written assignment coming out dealing with counting and enumeration, but we're also going to have some exercises dealing with conditional probabilities as well. Okay? All right. Any questions about this? No? Does that make sense? Try this out yourself. It's 110. So we'll go to the next slide and probably end here. So when we have a conditional probability, it's important to be able to work with these things. And here I've sort of plugged in the definition of what a probability, conditional probability is. And I really wish I had my pen. Maybe I'll pick back up on Tuesday with this so I can have a charged pen to actually write some stuff down on the slide. Since it ran out of power, it doesn't work. So probability of A given B, as we said before, is the probability of A and B, so that's the A part, over your new universe of consideration, probability of B, right? So that's our definition. So we can take this expression on top, and we see A given B is equal to something. If we multiply both sides of equality by probability of B, that copy of probability of B in the denominator on the right-hand side of equality goes away, right? Goes to 1. And what we're left with is probability of A and B is equal to the probability of A given B times probability of B. I just sort of reversed the direction of it. So that's sometimes called the product rule. And what that product rule expresses is a relationship between the so-called joint distribution, A and B, probability of, and the conditional distribution. It says the joint distribution between A and B is the same as probability of A given B, the conditional, A conditioned on B, times the probability of B alone, which is also called the marginal, the single variable probability. Likewise, we can do the same with probability of B given A, right? So we could say probability of B given A is equal to B and A over probability of A. And then we multiply both sides of equality by probability of A, and we get this expression. So in essence, we have 2 different ways that we can describe the joint distribution probability of A and B. And because and is commutative, it's the same regardless if you say probability of A and B or B and A, that's the same expression. And so there are 2 ways we can specify the joint distribution between A and B, probability of A and B. We can say it's equal to probability of A given B times probability of B, or we can say probability of B given A times probability of A, right? So we will continue on with that on Tuesday and use that to describe or derive rather a very important rule called Bayes' law. And Bayes' law is also another thing that's used very heavily in robotics and machine learning and other disciplines as it pertains to predictive analytics. Okay? All right. Any questions? No final questions? So with that, it is 1:13. 2 more minutes. I will end there, and I'll see you all on Tuesday.